Log on, tune in, find out. Another good idea from Cambridge.
Yeah, I would like to thank the organizers for inviting me to this nice conference and this nice place. So this is going to be Sarvesh talk. So the full survey and even a written article, they are available on my webpage. It's pretty long, so I'm not going to attempt to hurry through the entire survey. So I will probably cut it down to half of it and focus little more on 4 concrete problems. And these problems, they will be self-contained. You don't need to know any computer science to solve them, but if you solve them, it will really help computer scientists. And do interrupt me if anything is unclear. So this is going to be a talk about NP-complete problems. So here is a canonical NP-complete problem. It's called 3-SAT. So I assume most of you know this. So you are given a 3-SAT formula phi, which consists of Boolean variables x1 through xn. These variables take values either true or false. And then you are given a collection of clauses C1, C2 up to C sub m, and a clause is simply logical OR of 3 variables, either variables or in negated form. So here is a typical clause, and the formula is called satisfiable if there is a true false assignment to the variables which satisfies all the clauses, right? And the problem is NP complete, meaning unless P equals NP, there is no polynomial time algorithm that can distinguish whether a formula is satisfiable or unsatisfiable. Okay? And for every NP-complete problem, or most NP-complete problems, you can usually consider its optimization version. So in this case, you are given a formula phi, and you want to find an assignment that maximizes the number of clauses that are satisfied. And of course, it's NP-complete, so you don't hope to solve this maximization problem in polynomial time either. So instead, you could try to design what are known as approximation algorithms. So these are polynomial time algorithms, which for some constant c, think of it as being greater than 1. So this is called approximation factor. So these are polynomial time algorithms which, for a problem instance I, compute a solution a of I, which is guaranteed to be within factor c of the optimum. So if it's a maximization problem, then the solution computed by the algorithm is at least the optimal solution divided by c. So opt of I is going to denote the value of the optimal solution. If it's a minimization problem, then a of I is guaranteed to be at most c times the optimum. And here are some 3 approximation algorithms with the approximation factor. The first 2 are going to be trivial. So the clique problem on n vertex graphs. So the goal is to find the clique of maximum size. Now if it's an n vertex graph, the maximum clique can be of size at most n, right? On the other hand, here is a trivial algorithm. It just picks one vertex and declares that to be a clique, right? So that definitely achieves an approximation factor of n. So that's triviality. So max 3-SAT, so this problem. So here, let's say to every variable I assign true or false at random. Then each clause is satisfied with probability 7/8, right? So in expected sense, you satisfy 7/8 fraction of the clauses. You can always de-randomize this algorithm if you want. And the best assignment could possibly satisfy all the clauses, right? So this algorithm already qualifies as 8/7 approximation. And then there is a problem called set cover. So it's about points and sets and finding a minimum collection of sets which cover all the points, so on and so forth. This has algorithm with approximation factor of natural log of n. So don't worry if you don't know this problem. And surprising fact is that actually for these 3 problems, the three algorithms and the approximation factors that I described, these are the best possible ones. So unless P equals NP, there are no better approximation algorithms, right? And these are called inapproximability results or hardness of approximation results. And that's going to be the focus of this talk, the hardness results. So here is a hardness result, which one could call mother of all hardness results. So almost all known hardness results this is the starting point. It's called PCP theorem. PCP stands for probabilistically checkable proofs, but I'm not going to worry about that in this talk. So just think of this as the following hardness result. I give you a 3-sat formula like this, and the theorem states that it's NP hard to tell whether the formula is satisfiable or it's highly unsatisfiable, meaning no assignment satisfies more than 99% of the clauses, right? So this is the basic NP completeness result, which says that it's hard to tell whether the formula is satisfiable or unsatisfiable. So this is much stronger, right? It's hard to to distinguish whether a formula is satisfiable or highly unsatisfiable. And this definitely implies that this problem is hard, the maximization version of the problem is hard to approximate within factor something like 1.01, right? Because if you could approximate within factor 1.01, you could run your algorithm on this formula and distinguish between these two cases, which is supposed to be NP hard. So this is the hardness result, and all hardness results use this as a starting point. Yeah, so I already said that for max 3-sat there is this 8/7 approximation. Just take a random assignment, and that's the best. You can improve this to exactly 7/8. Or strictly speaking, any constant which is strictly larger than 7/8. 7/8 plus epsilon.
And that's sharp. 7/8 is sharp.
That is sharp because I already gave you the algorithm which achieves 7/8. Just take the random assignment. This is what I said, that for these 3 problems the factors are optimal. So for clique, you can prove hardness factor of n to the 1 minus epsilon. For max 3-sat, 8/7 minus epsilon. These are results by Hostad. And for for set cover, Feige showed hardness factor of 1 minus epsilon times natural log of n. Epsilon is arbitrarily small constant. Well, other than hardness results, there are many more exciting results in this area. For instance, in 2005, Dinur, she obtained a very nice combinatorial proof of the PCP theorem. The original one was using algebraic techniques. But still, there are many problems for which the approximability status is open. So here are some of the central open problems. So for vertex cover, there is a 2 approximation. Best hardness result is 1.36. For coloring 3 colorable graphs, there is an algorithm which, given a 3 colorable graph, produces a proper coloring using n to the 3/14 colors roughly. N is the number of vertices, which is pretty bad. On the other hand, we only know that it's NP hard to color 3 colorable graphs with 5 colors. So there is a huge gap, and there are similar gaps for sparsest cut, max cut, and so on. And this unique games conjecture, so this was proposed as a way towards making progress on these problems from the hardness side. So to prove better and better hardness results. And then in the subsequent years, turned out that the conjecture has many connections to other topics such as Fourier analysis, geometry, algorithms, and so there is a topic called parallel repetition in computational complexity, which I will try to describe towards the end. So I will try to highlight some of these connections. Okay, so what is a unique game? So the term game is little bit of a misnomer. I mean, it arose for some historical reasons. But just think of this as a constraint satisfaction problem. So here is example of a unique game. You are given a system of linear equations mod k. Think of k as a large constant, like 1000. And each equation has this very specific form: xi minus xj equals some constant. And the goal is to find an assignment to the variables that satisfies maximum fraction of the equations. So this is what a unique game is. And the conjecture is that this problem is very hard to approximate. Now, we don't really care so much about the fact that these are equations, linear equations modulo k. What we really care about is that each constraint has the property that, let's say the constraint is x1 minus x3 equals 2. It has the property that once you fix any value to x1, there is a unique value to x3 which satisfies the constraint, and vice versa, right? So this is the property we really care about. And
The
yeah.
system may be inconsistent, right?
Oh yeah. So in fact that is the interesting case. If the system is consistent, you can actually find the solution in polynomial time by Gaussian elimination, any of the standard methods. So actually the interesting case is when the system is inconsistent.
You want to satisfy as many of them. You know you can't satisfy all of them. It's an inconsistent system. You would like to satisfy as many of them as you can.
This is mod K. Simplex methods will not.
Yeah, but
get it.
it's like modular.
And there are only two variables in each equation.
Yeah, that's important. There are exactly two variables in each equation.
Why did you put k minus 7 there? That looks a bit odd.
Well, it's modulo k, so I allow any constant modulo k.
It's
Minus
minus
7.
7.
It's
It
minus
means
7.
minus 7
Right, it's positive.
to make you happy.
Just write it as
K
minus
minus
7.
7 and minus 7.
Okay. So actually, I'm going to define it as a little more general problem. It's actually useful to draw pictures and so on. So this is what a unique game is. It's a constraint satisfaction problem. So in this picture, the big circles, they represent variables. Okay? And the edges between these variables, they denote constraints between pairs of variables. It's a labeling problem. Meaning to every variable you want to assign 1 out of k labels. Okay, so in this example k equals 4, and the 4 labels, they are drawn as 4 little dots inside each circle. Right? So the goal is to pick 1 dot out of each circle. It's a labeling problem, right? So you want to find the labeling, and you want to satisfy as many constraints as possible. And the constraints are defined by matchings like this. So look at this constraint. There are 4 dots here, 4 dots here, and there is a perfect matching between the 4 dots on either side. And edges of this matching, they represent the satisfying assignments. Okay? Meaning, if you pick a dot here and a dot here, you manage to satisfy a constraint if that happens to be a matched edge. Okay? So that makes sense. Right. So here is a good labeling. So I picked 1 dot from each circle. That's colored as red, and all the red edges, red lines, they represent the constraints which are satisfied. So I managed to satisfy 6 out of 7 constraints, and if you really look closely, if you take this 4 cycle, then the 4 matchings along this cycle, they are perfectly inconsistent. So there is no way to satisfy them all simultaneously. So you must fail on at least one edge of the cycle, and I am satisfying 6 out of 7 constraints. So this is the best possible one. So in this case, the optimum is 6 over 7. And the unique games, these were considered actually at least a decade before, in the context of parallel repetition, which I'm going to describe towards the end. And the question we are interested here is how hard it is to determine or to approximately determine the optimal value of a unique game. Okay. Now, it's easy to see that if the optimal value is 1, meaning there is a labeling which satisfies every constraint, you can definitely find it very quickly. So here is why. So I can always assume that I know the label of this guy, because I will try all 4 and let's assume that I know the label of this. Now the label here uniquely determines the label here. The label here uniquely determines labels of all its neighbors, so on and so forth. So I can discover all the labelings very quickly. So if the optimum is 1, actually you can easily decide whether you can easily find this labeling. So the interesting case is when even the best labeling can satisfy only say 99% of the constraints. Okay? And then the question is how good a labeling can you actually find in polynomial time? And this conjecture states that actually this problem is very hard. So given any epsilon delta, there is a large enough integer k such that it's NP hard to distinguish whether a unique game with k labels has optimum at least 1 minus epsilon, or the optimum is at most delta. Or to rephrase, if I give you an instance, I tell you that there is a labeling which satisfies 1 minus epsilon fraction of the constraints, meaning almost all constraints. it's NP hard to find a labeling which satisfies even a tiny fraction of constraints, tiny delta fraction of the constraints. So that's the conjecture. Yeah, so sometimes a problem like this where the optimum is either very large or very small, these are called gap problems with a gap of 1 minus epsilon versus delta. So we are saying that this gap version with this particular gap is NP hard. And what is known is that instead of uni games, there are little more general form of games called projection games, and this result is known for these projection games. In fact, with a gap of 1 versus delta, and this follows from this PCP theorem and Raja's parallel repetition theorem, and this is actually the starting point of most hardness results. But I'm not going to talk about this here.
So k is equal to infinity. I mean, if you just do it not modulo k, but just on those.
You could even consider these as equations over integers. That is also fine. These all forms are equivalent to each other. You can even forget about actually the number of labels and just think of it as system of equations over integers. If you like.
For every epsilon delta.
Yeah, for every epsilon delta. Yeah. But actually, we will stick to k, some fixed number of labels. Okay, so this is a slide which is going to lead to the first open problem of this talk. So it turns out that this unigames problem is very closely related to finding small sets in graphs which do not expand. Okay, so let's see why. So here is a unigame. It has n variables and k labels. Now I'm always going to denote G as this outer graph, right, of the variables and the constraints, and G prime is going to denote this graph on n times k vertices, where inside each circle I draw these k labels and draw these matchings. So this whole graph will be called label extended graph with n times k vertices. Now the red vertices, they denote this best optimal labeling, and note that for this set, so let's give this set a name S. So this is the optimal labeling. The size of this set is 1 over k times the size of G prime, right? Because from each block I selected 1 out of k vertices. So its size is 1 over k, and it's not difficult to see that the expansion of this set, meaning the fraction of edges which are incident on this set that actually leave this set, is very small, because all the red edges, they start at a red point and come back to a red point, right? So the only edges that leave this set, they exactly correspond to the constraints which are not satisfied, right? Right. So the expansion of the set, it corresponds to the fraction of constraints which failed. Okay. So in particular, if it was a very good labeling, meaning the optimum was very close to 1, this is a set whose expansion is at most some epsilon. So it's a set that does not expand. So the unigames, roughly speaking, is about finding sets in graphs of size 1 over k which do not expand, roughly speaking. And in fact, that's now a conjecture. So Raghavendra and Steurer, they conjectured that this problem is hard, finding small sets in graphs which do not expand. So here is a concrete statement. For every epsilon, constant epsilon, there is a constant delta, such that given a graph G, it's NP hard to distinguish between the following two cases. Either there is a set of size delta times the number of vertices whose expansion is at most epsilon, or every set expands by at least 1/2. So either there is a set which does not expand at all, or every set expands really well. And the conjecture is that it's NP hard to distinguish between these two cases. Okay, and they show that this actually implies the unigames conjecture. So now the first open problem, this is going to be about existence of certain kind of graphs, and the existence of these graphs is implied by this conjecture. Okay, So I will describe what these graphs are, but let's see why this conjecture implies existence of these graphs. So roughly the idea is as follows. So the conjecture states that certain problem is hard. Okay. So I am going to propose an algorithm to solve this problem. Now the conjecture says that this algorithm fails. So it fails on some concrete instance at the very least, right? And that concrete instance is the kind of graph that exists. Okay. So I am going to propose an algorithm. So first observe that if a set is non-expanding, yes, so I'm trying to find this set whose expansion is at most epsilon. And let's one sub s denote the characteristic vector of this set. So its expansion is at most epsilon. So this is same as saying if G denotes the normalized adjacency matrix of this graph, then this is at least 1 minus epsilon times square norm of this vector, right? So roughly speaking, this implies that the vector 1 sub s, it should essentially be in the linear span of eigenvectors whose eigenvalue is at least 1 minus epsilon, right? So this should essentially be inside the linear span of vectors v1, v2 up to vm, such that these are the so m is these are the eigenvectors, and m is the number of eigenvalues that are at least 1 minus epsilon. So this is an observation. So here is my proposed algorithm.
So Subhash, perhaps it can be confusing. We were talking about the random walk matrix. If you want to do 1 minus epsilon, otherwise we try to confuse.
Normalize.
It's a normalized. Your normal, it's the normalized adjacency.
Yeah, it's normalized. Yeah, I said this.
So,
So one is the largest eigenvalue. Okay, so largest eigenvalue is 1. So here is my proposed algorithm. I compute the eigenvalues. Compute m, meaning I compute all the eigenvalues. I take those which are at least 1 minus epsilon. If m is too large, if m is greater or equal to, let's say, some n to the beta, I simply accept. And if m is less or equal to n to the beta, I know that the vector that I am looking for, it's in the linear span of these vectors. So this linear span is a subspace. I discretize it and I just do a brute force search on this subspace. So if m is less or equal to n to the beta, try to find this 1 to the s in the span of v1 through vm. If you find it, then accept, otherwise reject. Okay. So this is my proposed algorithm. Now I run this algorithm on this on this instance. So clearly, if there is a set whose expansion is at most epsilon, I'm going to accept, right? Because if I'm in this case, I always accept. If I'm in this case, I actually find it in the span and end up accepting. So if there is a set whose expansion is at most epsilon, I definitely accept, right? Therefore, if this problem is hard, there must be an instance which is of the second type, meaning every set expands by at least half, and on this instance the algorithm erroneously answers accept, right? Okay, so well, I should say that the running time of this algorithm is n to the beta. Running time is 2 to the n to the beta, right? Because there is, you need to search in this subspace of dimension n to the beta, you discretize it. So your brute force algorithm is going to take this much time. And there is a standard computational complexity assumption is that NP complete problems you cannot solve in time something which is like this. Okay, and therefore there must exist a graph which is of the second type and on which the algorithm erroneously ends up accepting. Okay. So yeah, so if you write down what this graph has to look like, so I wrote down the description. So this conjecture plus this complexity assumption implies the following: that for every epsilon there is delta and beta, and a large infinite family of graphs such that the graphs have large number of large eigenvalues, specifically at least n to the beta eigenvalues that are at least 1 minus epsilon, and every set of size delta expands by at least half. Okay. And the question is, do these graphs exist? And this looks like a very nice question. If you prove that these graphs do not exist, then you disprove this small set expansion conjecture. If you construct these graphs, well, I won't formally claim this, but I believe that if you construct these graphs, these will be actually useful to construct reductions and prove these small set expansion conjecture and unique games conjecture. Okay. So this is the first question. This makes sense? So here is another related.
Ordinary expanders don't satisfy the first condition.
No. So the ordinary expanders won't do it because I mean, for an ordinary expander, all eigenvalues are, well, except the largest one, they are strictly bounded away from 1.
Yes. Right. But the bound can be arbitrarily small. You have expanders with very small gap.
I guess you would need to look at the constructions and see.
The point is, you're saying that because you only got expansion for small sets, you can't deduce that the eigenvalues are small. So
I only care that the small set expands. So this doesn't necessarily mean that so the graph need not be an expander. I only need that the small set expands. So here is another result. It's a little bit hard to see why it is related to the topic of this talk. So this is about solving system of linear equations over reals. So imagine that you have a system of linear equations where each equation, each equation has 3 variables, right? And these are all homogeneous. So typical equation will look like x1 minus x3 plus 2x5 equals 0. And you are interested in solving this. So of course, you can assign 0 to each variable and you are done, right? But that's kind of cheating. So you are required to give me a solution which is non-trivial. So I'm not going to define exactly what non-trivial is. Let's say that you must assign to at least 1% of the variables a value which is at least 0.01 in absolute value, something like this, right? And here is a result that for such a system, it's NP hard to distinguish between the following 2 cases. Either there is a non-trivial solution that satisfies 1 minus epsilon fraction of the equations exactly, or the second case that any solution, any non-trivial solution, it fails on a constant fraction of equations with an error of at least square root epsilon, where error is defined as you evaluate the left hand side of the equation. So instead of 0, let's say it turns out to be alpha, then alpha is the error. And the connection to the this unique games problem is that so for a while we believed that we could actually start with this result, and so this problem one can call it as 3-lin R, linear equations over reals with 3 variables. So we for a while believed that we could reduce this further to a problem which is 2-lin R, which is the same problem but now equations have 2 variables, and that kind of is pretty close to what a unique game is. But I do believe that it will be useful to study linear equations over reals. Okay. So let's see this inapproximality results. So there is a long list of results now, which are of the following type: that if the unique games conjecture is true, then a problem is hard to approximate. And for many cases, you actually get hardness results which are exactly optimal, meaning there is in fact a matching algorithm which achieves the exactly same bound as an approximation factor. So I'm not going to show you this big list. Instead, I will sketch such a result for a problem known as max cut. So these results are proved by reduction from this unique games problem. And this type of reductions, these started in mid-90s with a paper of Bellare, Goldreich and Sudan. So I'm going to show you a reduction to a problem known as max cut. So this is a problem where you are given a graph and you want to cut it into two paths so as to maximize the number of crossing edges between the two paths. Okay, it's called max cut. So we will have a reduction, meaning reduction itself is an algorithm which takes a unique games instance and produces an instance of max cut problem, which is simply a graph, and it has the following properties. So the unique games instance, it's either highly satisfiable or it's highly unsatisfiable. Okay. If it's highly satisfiable, then this graph that we are going to produce will have a large cut. So there will be a cut of size rho. Think of rho as a parameter, something like 0.8. And if the unique games instance is highly unsatisfiable, then there will not be any cut that is larger than arc cos 1 minus 2 rho over pi. So this number actually happens to be significantly less than rho. So just take my word for this. So either there is a large cut or all cuts are small. Okay. And since distinguishing between these two cases is supposed to be NP hard by the conjecture, it implies that distinguishing whether there is a cut of size rho or there is no cut of size larger than this is also hard. Right? So max cut is hard to approximate within a factor which is ratio between these two numbers. And if I'm proving hardness results, it's in my best interest to pick rho so as to maximize this ratio between the two. Right? So you pick the optimal rho, and this ratio happens to be about 1.13. It's some exact constant which is supremum of some trigonometric function. So call this constant alpha sub GW. So GW stands for Gomans-Williamson, who actually gave an algorithm whose approximation guarantee exactly matches this approximation factor. So it's an algorithm based on something known as semi-definite programming relaxation, followed by a rounding algorithm. So we might get to it towards that. And these reductions, roughly speaking, they always look the same. So here is how the reduction looks like. So every unique games variable is replaced by a hypercube, a Boolean hypercube of dimension k. And then whenever there is a constraint between two unique games variables, there are edges going from one hypercube to the other. And that's the graph the reduction produces. So I'm not going to describe it in detail. So I just wanted to give you high level idea of how the reduction works. And then these two properties, right, we need to prove these two properties. These more or less follow from properties of this properties of hypercube, or rather properties of cuts on the hypercube. Okay. So I'm going to describe these properties. So we will be interested in cuts on the hypercube, and the cut on a hypercube is simply a Boolean function, right? So the graph is plus minus 1 to the k, and a cut in this graph is simply a function on this graph which is plus minus 1 valued, right? So we'll be interested in Boolean functions on the hypercube and their Fourier properties. Now, so somehow the reduction has to make sense, meaning if you intend to assign a label to a variable on the left hand side, so somehow that label has to correspond to some cut here, right? Now there are k labels, 1 through k, and k corresponds to dimensions of this hypercube. So the labels are actually going to correspond to dimensions of the hypercube and cutting the hypercube along specific dimensions. Okay. So we'll be interested in cuts which are cuts along specific dimensions, and these are called dictatorship cuts. So dictatorship function, well, cut you can again view it as a Boolean function. So the corresponding Boolean function will be a function of the type f of x equals x sub I, which corresponds to cutting the hypercube along ith dimension. And specifically, well, the graph that we are interested in is not quite the hypercube. The vertices are vertices of the hypercube, the 2 to the k vertices, but the edges are not quite the edges of the hypercube. So the edges I am going to define next. So it's best to think of this as a complete graph whose edges have weights, and the sum of the weights of the edges equals 1. So the weights you can think of as probability distribution on the edges. So I'm going to tell you how to draw an edge from this distribution, okay? And that's going to define the weighted graph. And the edge is defined by first picking a random vertex x of the hypercube and call it x, and then flip every coordinate of x with probability rho. Think of rho as about 0.8, and that gives you y, right? And that's how I pick an edge xy from this distribution. And this is typically known as noise sensitivity graph. So it's a weighted graph, right? With sum of all edge weights equals 1, and we'll be interested in cuts in this graph. So one type of cuts, these are the dictatorship cuts. As I mentioned, you cut the hypercube along a specific dimension. So what is the fraction of edges that are cut by this dictatorship cut? That's rho, right? Because if you cut along ith dimension, how many edges are cut? So edges are typically xy is an edge if y is obtained from x by flipping every coordinate with probability rho. So you are going to flip the ith coordinate with probability exactly rho, right? So these are cuts of size rho, and it's easy to show that these are actually cuts with cuts of largest size. On the other hand, well, this refers to the analysis of the reduction. So you need to worry about cuts which do not look like dictatorship cuts, or rather cuts which are far from dictatorships. Okay. So what do I mean by a cut which is far from a dictatorship? So dictatorship, if you view it as a Boolean function, then it's a function where that one particular coordinate is influential and remaining coordinates are irrelevant. So specifically you can define influences of variables on functions. So influence of ith coordinate on a function, this is the probability that f of x differs from f of x with the ith coordinate flipped. So these are influences of coordinates. For a dictatorship function, that specific coordinate has influence 1 and the remaining have influence 0. So we can say that a cut is far from dictator if the corresponding Boolean function has no variable with any significant influence, or rather all influences are negligible. So these are the cuts we need to worry about, and this is the question. If there is a cut whose all influences are small, how large can this cut be? And that's a very nice theorem called majority is stablest. This is the theorem of Mosel, O'Donnell and Oleshkiewicz, which states that any cut which has no influential coordinate has size at most this quantity. This is the same number that appeared before. This number is less than rho. Rho is the size of maximum cut achieved by the dictatorships, and it's larger than half. Half is a cut with the size of a random cut. And this somehow gives you the hardness result for this particular problem called max cut. And this reduction, there are similar reductions for many other problems. And for different problems, one uses different Fourier analytic theorem. So for this particular one, we use this majority stabilist. There are applications of many Fourier analytic theorems, such as a theorem of Kahn-Kalai, lineal. There is one by Friedgut, there is one by Bourgain, and so on. In fact, there is almost one-to-one correspondence between discrete Fourier theorems and their application to such inapproximability results. So I'm not going to describe these several Fourier analytic theorems. So instead, I will pose a concrete problem about Boolean functions on the hypercube. So the Mossel, O'Donnell, and Oleshkewicz paper, they also have another theorem. It's called it ain't over till it's over. Well, the reason for this name is Boolean functions, you can view them as voting schemes. And if you consider a voting scheme such that no voter has any significant influence, then result of an election is not determined until you have counted almost all the votes. So that's really the statement of the result. But here is a statement which is relevant for what I'm going to say next. So take a Boolean function. It's a non-trivial function. So let's say the expectation is 1/4, meaning on 1/4 of the inputs it's equals 1. Now imagine that you pick a random subcube of linear dimension, say dimension n over 100, and the function happened to be identically 0 on a constant fraction of such subcubes.
So what is a subcube exactly?
Yeah, so a subcube it's a subcube of dimension n over 100, meaning there are n over 100 coordinates which are free, and the remaining coordinates are set to some concrete values. Well, those will be chosen randomly, right? And the set of size n over 100, that itself will be chosen randomly. So, right? So imagine that. So assume that the function is identically 0 on a constant fraction of such subcubes. Then this theorem, the Mu theorem, it implies that the function must have at least one variable which has significant influence. Okay. Or in the contrapositive, if a function has all variables with low influence, then the function is, it cannot be identically 0 on almost any cube, any subcube. So that's the known theorem. So what's the conclusion that you get? That a function has variable with large influence. Now I am interested in a stronger conclusion. So for instance, I would be very happy if I could conclude that the function is actually very close to a junta, meaning it's a function which is very close to a function which depends on only a bounded number of coordinates. Junta is a function that depends only on some large constant number of coordinates. So now the answer to this is no, and you can look at this following example. So this is a hypercube. So first start with a dictatorship function. So it's 0 here and 1 here. Yeah, so now it's clear that the probability that the function is identically 0 on a random subcube is there is a probability 1 over 100 that the subcube will actually be partly here and partly here, in which case it cannot be identically 0. So with probability 1 minus 1 over 100, it will either be completely on this side or on this side. And with probability half of that, it will be completely on this side. Right? So this is the probability that the function is identically 0 on a random subcube. Now the same statement is going to hold even if I corrupt half of the values on the right hand side arbitrarily to 0. So corrupt random half of the values to 0 right? On the right hand side. So this gives you a function which has again the same property. Now clearly the function has influential variable, so this is the one, right? This is the coordinate, but it's not a junta, right? Because my corruption is completely arbitrary or random, so it's not a junta. Right? So yeah, so the answer to this question is no. However, let's say I had the flexibility to flip back the zeros which were corrupted back to 1, then I could turn it into a junta. Right? In fact, here I could turn it into a dictatorship. So that's the next this open problem. That can you always do this? So does there exist a G which is monotonically above F, meaning you can flip zeros to ones if you like, and G preserves the property that it's again 0 on essentially the same fraction of random subcubes, maybe a little bit less, and it's very close to junta of size t, where the t could depend on delta. So this question, I don't think this question, answer to this question is going to have any wider impact, but it looks like a very nice question by itself. So the next topic is algorithms, but I think in the interest of time I will skip this topic. There are several algorithms. So algorithms, these are to be thought of as attempts to disprove the unique games conjecture, right? Because the unique games conjecture states that a certain computational problem is hard. So if you actually come up with a good algorithm, you disprove it. So these are attempts, but they are partial attempts. They don't quite disprove the conjecture. But still, there are many nice ideas, and these algorithms, they do give some insight into the hard instances of the unique games problem, if the problem is indeed hard. So instead I will move to the next topic, which is the geometry. So even within geometry, there are at least 3 kinds of connections. First is connection to isoperimetric problems, and this connection arises from the Fourier analytic side. So for instance, this majority stablest theorem, which is about cuts on the hypercube, it actually reduces to isoperimetric question in the Gaussian space, and the problem is finding a partition of the Gaussian space into 2 equal parts, which minimizes the surface area of the boundary, and this was solved by Borel in early 80s, and that in turn implies the majority stablest theorem, and different theorems such as majority stablest, they lead to different isoperimetric questions. So that's the isoperimetric connection. So here I am going to talk about the integrality gaps and connection to metric embeddings. So what is okay, so this side we skipped. Okay, so what is an integrality gap? So fix a maximization problem of your choice. So let's say the max cut problem, and take an SDP relaxation. So I will say what an SDP relaxation is in the next slide. So think of it as it's some loose version of the problem that you actually want to solve. Okay? So the optimization problem will try to optimize over a certain space, and in the relax problem, you enlarge this space and maximize over the larger space. So if opt of G denotes the true optimum and SDP of G denotes the optimum or the maximum on this larger space, so clearly that's going to be at least equal to the opt, right? And the integrality gap is defined as the maximum possible ratio between the two. So take the supremum over all instances of the problem, the ratio between the two. So I will show one concrete relaxation. So here is the max cut problem which we saw before. So this is a problem where I am given a graph. Think of the vertices of the graph as numbers 1 through n, and I want to cut the graph into 2 parts so as to maximize the number of crossing edges. Okay. So here is the formulation of this problem as an integer program. So I denotes the number of the vertex. So to vertex I I'm going to assign a variable v sub I, which is supposed to be either +1 or -1, depending on which side of the cut the vertex lies. Right? And then my optimum is maximum value of this expression, sum over all edges ij, vi minus vj square over 4. So if I and j were on the same side of the cut, vi will be equal to vj, so you get 0 in the contribution. If I and j are on the opposite sides, you get contribution of 1. Right? So you are exactly counting the number of edges which cross the partition, and you want to maximize this. Now this is just a formulation, another reformulation of max cut. So this is again NP-hard problem to solve. But then you can take this SDP relaxation, and what the SDP relaxation allows you to do is, originally the variables are supposed to be +1 or -1. Now the variables are allowed to be unit vectors in arbitrarily high dimension. Okay. So in particular, +1 -1 is a special case, right, where you have two vectors in opposite directions. Right? And you write down the same program again. Now these VIs are allowed to be unit vectors, and then you maximize the same thing. So instead of absolute values, you take normed square, L2 normed square. And the point is that this program, this can be solved essentially in polynomial time, up to arbitrary degree of accuracy. So this you can solve. Okay. But since it's a relaxation, this value will typically be larger than the true optimum. Right? And if you recall, integrality gap is the maximum ratio between the two. And for this problem, it's known. So these are results of Gomans-Williamson and Feige and Sheckman, that the integrality gap is exactly this constant alpha sub GW that appeared before. It's about 1.13. Now imagine that you are an algorithm designer and you really care about better and better algorithms. Now as an algorithm designer, it's in your interest to reduce this gap. Right? So one way to achieve it is to add more constraints to this semi-definite program. And you are allowed to add a constraint as long as you are guaranteed that the constraint will be satisfied by ±1 valued solution. Right? And you can add polynomial number of constraints because you want to solve it in polynomial time after all. Right? So the number of constraints that you add, that should be polynomially bounded. So I'm going to propose new set of constraints which could be added in principle. So what are these new set of constraints? So let's again restart with this original formulation. So this is maximum. Now in the variable vi, I really want to think of it as v sub singleton set I. So you will see the reason. And I am going to have additional variables for every set of k vertices. So for every set A, subset of 1 through n. So 1 through n denote the vertices. For every set of size up to k, let's even fix some k equals maybe 15. For every set of size k, I am going to have a variable called v sub a, and this is also supposed to be +1 -1. And what is the intention of this variable? So this variable is supposed to be product of the variables vi, I in A. So this makes sense? Right, so the vi's are the original variables, and for any set of size k, take these are +-1. So you can, for any subset, you can take product of the signs over that set, and these are these new variables. Okay. Now you can add constraints. So here is a constraint that you can add for any 4 sets A, B, C, D, such that asymmetric difference B equals symmetric difference D, VA times VB equals VC times VD. I mean, this is obvious, right? Now this you can turn it into a semi-definite program, because now all these VAs, if I think of them as vectors, this last condition is a linear condition on pairwise inner products of vectors, and those are precisely the constraints that can be added to an SDP. Linear constraints on pairwise dot products of vectors. Okay. So that will give you this new SDP. Well, it's exactly same as I wrote here, except that now all these VAs, they are unit vectors, and the product is replaced by the inner product. Okay. And how many constraints there are? K, if you think of K as a constant, then there are n to the K constraints. So that can be solved in polynomial time. And this is the open problem 3. So is this, does this improve on the integrality gap? Can you show that the integrality gap is strictly less than this alpha sub GW? If you show this, then actually you disproved the unique games conjecture, because the unique games conjecture implies that beyond this, no approximation algorithm can achieve a guarantee beyond this, and in particular this one, right? But it seems, yeah.
K equals 5 there and K equals 15 over there.
It doesn't matter. So yeah, so this is open even for K equals 5, maybe even 4.
There's some computational results. So you can check it actually. If you add those constraints, then it's better, it's closer, so the gap is smaller.
Cannot be worse.
Cannot be worse, but
No, how would you check it, right? Because the class of graphs is infinite. So
But the obvious question is, why do you believe that those constraints are somehow useful ones to put in?
okay, so I was going to say next. Okay, so why is this even useful? Right? So the reason is that these are actually very natural constraints which are actually pretty strong, and even constraints which are weaker than this, meaning those that are implied by this, they are already useful in some algorithms. So instead of max cut, you consider the problem sparsest cut, and you can do precisely the same thing, and you can introduce constraints known as the triangle inequality constraints, which are implied by this, even for K equals 3, I believe. And once you do this, you already get better algorithm for this sparsest cut problem. So this algorithm of Arora Rao Vajirani, which gives square root log n. So the approximation factor improves from log n to square root log n. Right. And for just for that triangle inequality constraint, and even some additional constraints known as Sherali-Adams constraints, it's actually possible to prove that the integrality gap still stays exactly at alpha sub GW. Okay. And results of this kind, their equivalent formulation is in terms of non-embeddability result. So for instance, you can show that there is endpoint negative type metric which requires distortion at least log n to embed into L1. Or even stronger, there is endpoint negative type metric such that every subset of size log n embeds isometrically into L1, but globally it does not embed into L1 with distortion even log n. So results of this type. So these are nothing but integrality gaps like this. And the next slide will at least give a hint as to how these integrality gaps are constructed. Yeah.
Also, if you add these constraints for K large enough, do you get the exact value?
Yeah, so if you take this K to be actually equal to n, then it boils down to actually the integer program, and then you get the exact optimum. Okay, so how to construct these integrality gaps? So one way to do this is to construct integrality gap for the unique games problem, okay, and then reduce that integrality gap instance to gap instances for other problems such as max cut or sparsest cut using the reduction that we saw before. Okay. Yeah, it doesn't matter if you don't recall what we did before. But the starting point for this trick is to construct an integrality gap for unique games problem to begin with. So I'm going to describe what integrality gap instance for this unique games problem is, and that will be the last open problem. So do I have a minute? So forget everything and just look at this geometric picture on the right hand side, and you only need to understand it in geometric terms. Okay. So this is what this construction looks like. You have a graph. At every vertex of the graph, you have a k tuple of orthonormal or mutually orthogonal unit vectors. Okay. Right. Now imagine that you hold this tuple in your hand and you walk from vertex to vertex. You take a walk on this graph. Okay. So you have two properties. The first property is that as you move along an edge, your tuple, it only changes very slightly. Okay. So it rotates by just a little bit. Okay. So as you move along this graph, the movement of this tuple as a whole is very continuous. Okay. But then imagine that out of each tuple, you try to pick one vector as a representative. Okay. Then the movement of the representatives, it becomes discontinuous almost everywhere. So this makes sense?
So when you move along an edge, then the set goes to the same set?
Yeah, the set goes to the essentially the same set.
Not the same labeling.
Yeah, so this u1 through uk will go to v1 through vk, but the mapping will be some permutation between k indices there and k indices there, right? And it happens along every edge, but if you try to pick one vector from each tuple, it becomes completely discontinuous on almost every edge. Okay. Yeah, and you can concretely construct this this configuration, and that's what counts as integrality gap for the unique games SDP. And the open question is this: so in this construction, the size of the graph itself happens to be exponential in k. So is that necessary? No, I didn't tell you the construction, but if you try to think about it, it's fairly natural one. You will find it yourself. But it's very likely that the one you will find will be identical to the one we found, and it will be of size 2 to the k. That's the open question. Yeah, that's it.
Sorry.
Are there any questions?
Hi, Paris. Hi, Subhash. I have a question.
Yes.
When you stated the unique games conjecture, you mentioned a related problem, the gap projection game, gap 1 delta problem. Yeah?
Yes.
So what is this? Can you explain this gap projection game?
Yes. The question is, I mentioned something known as gap projection game. So what is that?
Yeah.
So the gap
Mute it when you're talking. Mute it when you're talking, so we don't hear you again.
So the gap projection game is very similar to the unique game, except that on one side the variables can take 1 out of k labels. On the other side, the variables can take 1 out of, let's say, 100 times k labels. And for every label on the right hand side, there is a unique label that you can place on the left hand side. So that's what a projection game is. So there is a projection from 100k labels to k labels. Does this make sense?
Every pair of vertices, yeah?
Yeah.
I see. And how come this problem is known to be hard, whereas the unique games problem is not known?
Yeah, I mean that doesn't have a short answer. Right?
No, but these are different problems. Explain the difference.
Well, I mean these are different problems, right? So unique games is a special case of the projection game.
Yes, it's a smaller class.
Yeah, it's a smaller class. So the larger class is hard,
Yeah.
but the smaller class is not known to be hard.
Yeah. Okay, thank you.
Thanks. I think you had a question?
This is just a very naive question.
Yeah.
Is it conceivable that unique games could have some intermediate level of difficulty between P and NP?
Yeah, that's perfectly possible. Yes.
What sort of heuristic reasons for that? Likely or something?
No, so it's perfectly possible.
So what was the question again?
That whether this unique games problem could have complexity which is between P and NP complete. So for instance, it's possible that the problem has algorithm that runs in time, say n to the log n. That's possible. And there is no reason to believe one way or the other.
Any more questions?
Yeah, just a small comment which may be useful to some people here. Just to mention that in this picture that we see now, the big graph has a covering map on the base layer. So conceivably there is some more geometry going on here, but I don't know that anyone has been able to do anything here.
Any more questions? So let's thank Subhash.